Hello, good evening.
Good evening,
Good evening,
Professor.
sir.
Good evening, sir.
Let me share the screen.
Good evening, sir.
Good evening, yes.
Good evening, sir.
So, in until yesterday, we have looked at the failure theories for ductile materials. In today's class, let us look at the failure theories for brittle materials. You are able to see the screen, I suppose.
Yes,
You
sir.
are
Yes,
able
sir.
to see? Yeah. Okay, great. So now, first of all, when we are defining failure itself, what do we mean by failure in the case of ductile material? What do we mean by failure in the case of brittle materials? In the case of ductile materials, the onset of plastic I'm sorry, the internet connection seems to have some issue.
Good evening, sir.
Yeah. So let me reshare the screen. Yeah. So you're able to see the screen now?
Yes, sir.
Yes, sir. So we were discussing what do we mean by failure. So yesterday we have looked at the failure in the ductile materials until yesterday. Now we are talking about failure for brittle materials. Whenever we are talking about failure, the definition of failure itself is different for ductile materials and brittle materials. For example, in a ductile material, the moment the component's stress state reaches a state where the component starts plastically deforming. That means the onset of plastic deformation itself is considered failure for ductile materials, because that leads to shape change and that results in the problems with the functional delivery of the functional requirement of the component. That is why for a ductile material, you consider onset of plastic deformation as the failure. Whereas for brittle materials, we cannot observe appreciable plastic deformation. As a result, the material, almost until it breaks completely, there will not be any plastic deformation. The material deformation is completely elastic. And as a result, the failure consideration for a brittle material is the complete breakage, which happens at ultimate strength of the material. Because the brittle material, there is no plastic deformation, and hence there is no concept of yield strength. You will only have ultimate strength of the material at which the material will have maximum load carrying capacity, and after that it will break. So Now, if you look at this particular guy, these two images, this is a ductile material, and on the right hand side you have a brittle material, which is, let us say, on the left hand side you have a mild steel specimen, on the right hand side you have a cast iron specimen. And if you apply uniaxial tension on both of them, you can see whenever the ductile material breaks, until breakage if you do, the breakage happens in a cup and cone at an angle 45 degree. That is because the plastic deformation happens first along a 45 degree angle. Why would the plastic deformation take place on a plane along 45 degree angle?
Because of shear stress.
Because shear stress is maximum on that plane. Right? The plane which is oriented at an angle 45 degrees to the loading axis is the plane in which you will have shear stress, maximum shear stress. So, since this plane is subjected to maximum shear stress, it is very likely that the same plane is going to break when it goes beyond the ultimate strength. That is why you have a 45 degree plane. And now coming to the brittle material, when you are applying the load, actually, brittle materials will not have any plastic deformation. So that means there is no shear effect. Brittle materials fail by fracture, and as a result, they are limited by their normal strength. That is why if you take a chalk piece and if you apply a load, chalk piece is a brittle material, right? If you apply a load axially and then it breaks normal to the surface, you can see here. It may break at the center any point depending upon, here probably because of the stress concentration it broke here. The idea is that it is breaking normal to the surface. Why is it breaking normal to the surface? Because on that plane, you have maximum normal stress, right? Because that is the principal stress and that is the maximum normal stress along x-axis. So because that is the plane to which the normal is x-axis, so sigma x-axis is maximum on that particular plane, and hence the failure happens on that plane because the brittle materials are limited by their normal strength. So similarly, in compression, differently. So we will talk about them later, but focus on this. So we have to understand that the brittle materials do not yield, they rather fracture. And for brittle material, fracture in tension is only due to normal stress. Because now the failure is completely governed by normal stress, whichever plane has maximum normal stress, that plane is going to break apart. So now, because the guiding line or the critical stress is the only normal stress, so now we need to use maximum normal stress theory. Because the maximum normal stress theory says what? On wherever the maximum normal stress reaches the critical value. Here the critical value will be ultimate strength rather than yield strength. So the maximum normal stress theory can be applied for brittle fracture in tension. Now for compression, you can see that it happens due to a combination of normal stress and shear stress. The failure happens. And so brittle fracture in compression is due to a combination of normal and shear stresses. And hence it requires a different theory. You cannot use the same theory that you use for normal tension. So depending upon the type of loading, you have to use a different theory. Okay. So in the normal, when the loading is tensile, the failure can be completely governed by the normal stress theory. Whereas when the loading is compressive, then the failure is not governed by the normal stress alone. The effect of shear stress also comes into picture. So this is something that we have to keep in mind. And when, particularly for even materials, if you take the example of a chalk piece, you do this thought experiment. When you take the chalk piece and apply a load, then it is easy, you will break. But if you apply a compressive force, it is extremely difficult to break it. Which means the ultimate strength in tension and compression are not the same. Unlike what we have assumed for ductile material, wherein you said yield strength in tension and compression are the same. But now their yield strength we are using because that is the critical value that we are looking for. Here, in the case of brittle material, the critical value is not yield strength, but ultimate strength. Now, we see that if you take a brittle material, the ultimate strength in tension is going to be much less compared to the ultimate strength in compression because it's much difficult to break it when it is under compression. So now you have a material whose critical value of stress with which you are qualifying whether the material is breaking or not seems to depend on whether the state of stress is tension or state of stress is compression. And hence we now define two materials called even materials and uneven material. So even material is one in which both the compressive strength is equal to the tensile strength. If a material has same compressive as well as tensile strength, such a material is called even material, like what we have seen for ductile materials. Uneven material means the compressive strength is not equal to tensile strength, which is typically the case in the case of gray cast iron, in which the compressive strength is almost 3 times the tensile strength. Okay, so this is because you have in castings, you have several microscopic flaws and they become fracture. So it's much easier to break open a crack rather than under tension rather than under compression. That is why under compression, they will have much higher strength. Okay. Sometimes some metals also show uneven response in yielding, but let us not worry about that at this point of time. So now, if you take a ductile material, okay, instead of applying tension, if you are applying torsion, that means pure shear. You see in the previous case, when you are applying uniaxial tension, the failure happened at an angle 45 degrees. But now if you are applying torsion, the failure happening normal to the surface. Can you explain why would it happen normal to the surface?
Because shear stress is maximum at normal to the.
Because you are applying pure shear, then the to this plane you will have your maximum shear stress is going to be in the same plane. That is why it is happening on the same plane, the maximum shear stress, isn't it? Because you are applying shear stress and the maximum shear stress is going to be on the same plane. That is why the failure happens normal. But if you take a brittle materials are governed by their maximum normal stress. So if you are applying torsion, the normal stress is going to be maximum at an angle 45 degree. Because if you draw the Mohr circle for a pure shear will be centered on the origin of sigma tau plane, and the maximum normal stress will be at an angle 90 degrees to the maximum shear stress. That means it is 45 degrees in the physical plane, so it will be at an angle 45 degree. The normal stress is maximum here. That is why the breakage happens at an angle. If you take a brittle material and apply torsion, okay. All right. So now, if you would plot your Mohr circle for the case of failure. So let us say if you are doing a tension test and this is your uniaxial tension test, this is your ultimate strength. Okay. When you are applying ultimate strength on the tensile side, the same, this will be your Mohr circle failure surface. And you know, on compression also, if it is an even material, the ultimate strength is same as tension. Then on the compression side, this will be your Mohr circle. Then the line joining, the tangent drawn between these two circles will represent the failure line. So any circle, any intermediate stress state, as long as that is not becoming tangent to this line, that will not fail. Otherwise, it will fail. Okay, that is the idea. Now, if you have a uneven material like here, where you have this guy is under tension, let us say under compression, you have larger ultimate strength. Then it is like pushing this fellow, and then this line is your failure line, and whose angle is mu. This is what we call friction angle. And now we can write the equation of this line as this is now sigma tau plane. On sigma tau plane, earlier we have written failure theory on sigma 1, sigma 3 plane. We could also have written on sigma tau plane. So now if you write it in sigma tau plane, because it's much more easier to write for brittle materials on sigma tau plane, you see that the failure line is given by tau is equal to tau I plus mu sigma, where tau I is this, wherever this line intersect the tau axis. Okay. So the shear stress is equal to tau I plus mu times sigma is your failure line. And this tau I depends on the size of these circles, isn't it? If you reduce the size of the circle, then the tau I becomes smaller. So this tau I is sort of a representation of your, this is somehow dependent on this radius and that radius, right? Here you are talking about an uneven material whose ultimate strength in compression is larger than ultimate strength in tension. Any questions here?
Sir, one small question here.
Yeah.
The failure line, what you're showing over here,
Hmm.
what you're trying to say is that that is the minimum shear stress required to create a fracture, right? Or a failure.
No,
And
the
anything above,
combination of not only shear, the combination of tau and sigma, this is the failure line, right? If you
Yeah.
are having a two-dimensional state of stress, you will get some shear stress and some normal stress, right?
yes,
If that combination satisfies this equation, that means if you draw the Mohr circle for that, so for example, let me give you, let me go back to my whiteboard. So today is 28. Yeah. So all that I'm saying is, let us say this is my sigma tau axis. Okay. Now let me say that my failures, if I am doing uniaxial tension test, okay, if I am taking a specimen, I am doing uniaxial tension test. If it is a brittle material, sigma epsilon will be like that, and that is my ultimate strength, sigma ut. That is where failure happens. At that time, it breaks like that, right? Let us say I have applied that sigma ut, and that sigma ut value is that. The sigma ut value is this. If it is same in tension and compression, so this is sigma ut, this is minus sigma ut, okay? Which is equal to sigma uc. Sigma uc is equal to minus sigma ut. Ultimate strength in compression, ultimate strength in tension. To avoid some confusion, in this work we use S. That is the boundary value. Now, if let us say I am doing a uniaxial tension up to this is the test and applied stress is sigma is equal to SUT. So that is the maximum principal stress. Then if I draw the Mohr circle, that's how it looks like. Do you agree?
yes.
So the same Mohr circle will be there on the left side. So this is because if you are doing compression, because I am saying that the same under tension and compression, it has same value. So under compression, the Mohr circle will be same. Now, these are the extreme limits, right? Under only pure tension, this is the Mohr circle. That means whatever stress state that I have, I cannot be beyond this Mohr circle. In pure tension, in pure compression, this cannot be anything beyond this. Is that concept clear?
Yes, sir.
Yeah. Now, if I draw a line tangential to these two circles, right? And that is what I call, this is basically a failure line. So this failure line intersects this fellow at tau I. Right? So if I have to write for an even material, the equation of this failure line, what do I write? My equation for failure line will be tau is equal to tau I. Isn't it? When my tau becomes tau I, when my shear stress becomes tau I, that is when failure happens. That is the equation for the failure line. What is the meaning of that? Let us say I have applied on the body, the stress applied is this much. Sigma, let us say that is sigma ut by 2. That is this, right? That is this value. All of you agree? Then for that particular uniaxial state of tension, what is the Mohr circle? The Mohr circle right? So, or this is maybe that is my tau max. So, what is the tau max value here? Tau max is less than tau I or not in this case?
Yes.
So, that means it does not fail. You can also have a scenario, it's not a uniaxial tension, but let us say you have, let us say sigma ut is equal to 300, right? So, this is 300. So, if it is 300, what is my tau max? This tau I will be what? If it is 300.
150.
So this is equal to 150. Let us keep it that way. Now I am applying a loading scenario wherein, okay, principal stress sigma 1 is equal to 150, sigma 2 is equal to 100. Okay, or sigma 2 is equal to 100. So when sigma 1 is 150, that is this point. I am just zooming in. And sigma 2 is 100 means somewhere here, isn't it? Sorry. Sigma 1 is 150. That means my first principal stress is this. I am drawing it with blue color. That is my that is my 150. Do you agree? And that is my sigma 1. What is sigma 2? 100.
100.
That is sigma 2 is what? 100 means somewhere here. Correct? Then my Mohr circle will be this. Will it fail?
No.
No, it will
No.
not fail.
Let us say sigma 1 is equal to 150 and sigma 2 is equal to minus 100 or minus 150 to make our life simple. So that means this is our sigma 2, right? In that case, if I draw my Mohr circle, what happened? Then that Mohr circle is just touching the surface. So that means it is failing, isn't it?
Yes, sir.
If I have instead of minus 150, if my sigma 2 is equal to, so let us say sigma 1 is equal to 200 and sigma 2 is equal to minus 150. Right? What is the tau max here? Our requirement is tau max is how much? 200 plus 150 by 2. Isn't it?
Yeah.
350 by 2, that is 175.
175.
What is tau I? 150. So now 175 is greater than 150. So that means this has failed, right? Because this tau I is 150, no? So now let us draw these things. 200 and minus 150. 200 will be 150. Let us say this is 200 and minus 150. Let me draw that particular circle. What happened? This circle went beyond that failure line, isn't it?
Yes, sir. Yes, sir.
So that means it has failed, and which we actually were able to see from here. So the point that I'm trying to make is, if you identify the failure line, if a material is failing, then the corresponding Mohr circle should become tangent to the circle at best, or it should not cross the circle, cross the failure line. If it crosses the failure line or it becomes tangent, if it becomes tangent to failure line, then the factor of safety is 1. That means it has just failed. But if it is crossing the tangent line, then the factor of safety is less than 1. If it is under the failure line, then the factor of safety is greater than 1. So now, in the same picture, let us take the scenario of uneven material. So if you have an uneven material whose failure surface is, this is, let us say, sigma ut or SUT, and SUC is double that. This is my SUC. UC, that is equal to minus 2 times SUT. In this particular case, it is double. Now, if I draw the Mohr circle for uniaxial tension case with SUT, let me draw that again. Oops. Happened. So that is my uniaxial tension case Mohr circle. And similarly, uniaxial compression case, so that is the Mohr circle for uniaxial compression. Now, how does the failure surface look like? That should be tangent to these two lines, right? So now I need to draw a tangent. Right, I have drawn this tangent, and this tangent intersects at this point. Let me call that as tau I. And the slope of this line is, I am calling mu. And this axis is sigma, and that axis is tau. Now, the equation of this line can be tau is equal to y is equal to, tau is y, m is mu, x is sigma, plus y-intercept tau I. Right? So I can write tau is equal to tau I plus mu sigma. That is the equation of this failure surface. Now, whenever you are taking any stress state, you plug into this equation, and if the stress state satisfies this equation, then it is failing. If it is less than, tau is less than tau I plus mu sigma, then it is safe. Otherwise, it is not safe. Or in other words, if you plot sigma 1, sigma 2, let us say this is my sigma 1 and that is sigma 2. Then if I draw a Mohr circle, and this is inside that the failure line, and hence it is safe. But let us say, when will it become unsafe? Let us look at that. Okay. So sigma 1 is same, but let us say sigma 2 is changing. So when the sigma 2 will become this value, you can see that is when the circle is becoming tangent. So if you have sigma 1, your sigma 2 cannot be greater than this value, because beyond this value, the circle is going to cross the failure line. So your sigma, given sigma 1, your sigma 2 should be less than this value. Only then the material will be safe, otherwise it is unsafe. Is that clear?
Got it, sir. Got it.
Any other questions here? Sorry, yeah. I'll just stop the screen and then reshare my presentation. Good.
Sir,
Yeah.
here this even material, does it mean ductile material?
Ductile materials are in general even. Some ductile materials can be odd or uneven materials. Most of the brittle materials are uneven materials.
Okay, sir. Thank you.
Yeah. All right. So, any other questions? Any other questions? So if there are no further questions, then let's move on. So the concept, this is your failure equation or failure theory for brittle surfaces. So typically so this is pure tension, uniaxial tension, uniaxial compression, and you can also do a pure shear test. This is pure shear. You can see that at you can have the maximum shear stress here. Then in the case of pure shear, sigma 1 is equal to minus sigma 3. Then you have the Morse, this failure line, instead of, because if it is two circles, then you can draw a straight line. But ideally what you should do, you should also do a shear line. Then you should draw a curve, common curve that is tangent to all these three circles. Okay. So then it will not be a straight line, it will be a curve, which is called failure curve. And this failure curve is called Morse failure curve. And this is what we call Morse hypothesis. Okay. So now let us look at the theory for brittle materials. This is what we call Mohr-Coulomb theory. So now let us say this is your uniaxial tension curve, tension circle. This is your uniaxial compression circle. Any questions there? And now, once you have the uniaxial tension circle, uniaxial compression circle, you can draw a Mohr-Coulomb line or the failure line, and that decides what is my tau I and so on. Now, if you draw a stress state corresponding to sigma 1 and sigma 3, and the fact that this circle is becoming tangent to this fellow, that means it is failing, right? So now let us look at the stress state corresponding to sigma 1 to sigma 3. Now let us carefully look at this fellow. I am drawing a tangent to this failure surface for the big circle, and that intersected C3, which is for the compression circle, and here B1 C1, which is at an angle 90 degrees from the center. B2 C2, C2 is the center of this pink circle. Now you can see that OB1 C1, OB2 C2, OB3 C3 are similar triangles. So when you have similar triangles, you can write this equation: B2 C2 minus B1 C1 divided by OC2 minus OC1. That must be equal to Yeah.
How did we draw the third circle?
Third circle is a state of stress, which is not pure tension and pure shear, but that state of stress corresponds to a stress state sigma 1 and sigma 3.
Okay.
And we have chosen that in such a way that that actually also fails. That is why it is becoming a tangent to the circle. Okay. Because the moment it becomes tangent to the circle, that fails, no? That is a failure line. It is becoming tangent. So this circle represents a state of stress that is actually failing under this combined loading. Is that clear?
Thank you, sir. Yes, sir. Thank
So now I am writing this equation is actually using the similar circles. B2C2 minus B1C1 by OC2 minus OC1 is equal to B3C3 minus B1C1 by OC3 minus OC1. Is there any question there? This equation is pretty straightforward, isn't it?
Yes, sir.
So now B2C2, what is the value of B2C2? This is the radius of this pink circle. That is sigma 1 minus sigma 3 by 2. Do you agree or not?
Yes.
The radius of the pink circle is sigma 1 minus sigma 3 by 2. So that is what is B2C2. Minus B1C1 is the radius of this circle, which is nothing but ST by 2, because from here to here ST, that is the diameter of the circle. So ST by 2 will be B1C1. That is what is plugged in here. And OC2 minus OC1. OC2 minus OC1. So similarly, I will come here. Please give me a minute. And the right side B3C3 is SC by 2 minus B1C1 is ST by 2 and OC3 minus OC1. So OC3 minus OC1 can be written as SC by 2 plus ST by 2, because SC by 2 is, if you start here, OC3 minus OC1, we are actually talking about this distance, C1 to C3 distance. Is that correct or not?
Yes, sir.
Yes.
So C1 to C2, C3 distance is this distance plus that distance. This is SC by 2 and that is ST by 2. Is that clear? The distance between C3 and C1 can be seen as distance between C3 to origin and 0 to origin to C1. So origin to C1 is ST by 2, because this is the radius of this circle. C3 to origin is the radius of this big circle, that is SC by 2. That is what we have written. Okay. Next, OC2 minus OC1, we are interested in the distance between C2 and C1. Correct? So the distance between this guy and this guy and the radius of this fellow, C2, 1 minute, OC1, right? OC2 minus OC1, that is nothing but
Distance
C2
between C1 and C2.
distance between C2 and C1. How do you identify that? That is, yeah. So if
ST
you
by
take
2.
this, from here to here the distance, that is ST by 2. And if you take minus sigma 1 plus sigma 3 by 2 is what?
C2.
Sigma 1 plus sigma 3 by 2 is C2. Then that gives you the effective distance between that, because this is counting this additional distance also. Okay. You can verify that at a later stage. Once, if you have questions on how do you get this, you can actually verify that by doing the geometry. And now if you simplify this equation, what we get is sigma 1 by ST minus sigma 3 by SC equal to 1. If you carefully observe this, if SC is equal to ST, what happens? If ST is equal to SC, so let us say SC is equal to ST, then what will this equation be?
Sigma 1 is equal to minus sigma 3.
Sigma 1 minus sigma 3 is equal to ST. Sigma 1 minus sigma 3 is equal to ST. Isn't it? SC is equal to ST means denominator is ST. So sigma 1 minus sigma 3 will become equal to ST. Do you agree?
Yes.
Yes.
Keep that in mind.
The failure line will be parallel.
So sigma 1 minus sigma 3, if you look at your maximum shear stress theory, this is what our equation is. This is our sigma 1 minus sigma 3 is equal to sigma y. There we are using ductile material, so we have used yield strength. But now instead of yield strength, what is showing up there? If it is a even
Ultimate strength.
material, ultimate tensile strength.
Ultimate.
Ultimate tensile strength. But the equation remains the same, isn't it?
Right, sir.
Sigma 1 minus sigma 3. So there is a similarity between maximum shear stress theory and Mohr Coulomb theory, except that it is an uneven material and hence it becomes sigma 1 by ST minus sigma 3 by SC equal to 1. So what we have done, why we have chosen this pink circle? Because this pink circle is also a failure surface. So when failure happens, this equation will be satisfied. Right? Sigma 1 by ST minus sigma 3 by SC should be less than 1 if the material is safe, or equal to 1 or greater than 1, the material is unsafe. Okay? This is what we call Mohr Coulomb failure theory. Now, I will not draw this line for you. So ST is ultimate strength in tension, SC is ultimate strength in compression. Okay. So now let me, without spending much time, we remember how we have drawn our failure surface for maximum shear stress theory, right? For maximum shear stress theory, the way that we have drawn the failure surface is this is my sigma 1, that is my sigma 3. Okay. Now, in the first quadrant, because that is my sigma y and that is my sigma y. 1, 2, 3. And here this is sigma y. This is how my maximum shear stress theory looked like, right? This can be written as sigma 1 by sigma y minus sigma 3 by sigma y is equal to 1. Can I do that? That implies sigma 1 minus sigma 3 is equal to sigma y. That is how we have generated this. We have discussed how we got these lines, correct? All of you agree with this or not?
Yes, sir.
Yes, sir.
So
Yes, sir.
now,
Yes, sir.
yeah. So now what I want to do is sigma 1 by, instead of sigma y, ST minus sigma 3 by SUT equal to 1. That is what I wanted to deal with. So all that I need to do, let us say this is my, this is also my SUT. But SUC this one. SUC is greater than SUT. So let us say that is my, in the negative direction, I have to identify SUC. And this is my SUC. For each, both of them are normal stresses, no? And this is my SUT. Agreed? So now in the compression side, when both are negative, because it is an even material, this will be bounds are sigma y and sigma y. I have drawn these lines, but now it is different value. Then I would draw this. Okay. On the tension side, it will remain this because that is SUT. Okay. And now these slant lines will be between this fellow and that fellow, just by looking at this equation. So now my failure surface for, I'm deleting this just to avoid confusion. So now you will see that it's also a hexagon, but it is a asymmetric hexagon. Previously, you had a symmetric hexagon at an angle 45 degree about the origin, but now you have an asymmetric hexagon because ultimate strength in compression is larger than the ultimate strength in tension. So this is how the failure surface for Mohr Coulomb theory looks like. This is what we call Mohr Coulomb theory. In the principal stress space, this is the equation. In the sigma tau space, the equation is tau is equal to tau I plus mu times sigma. So you can write the failure theory either in principal stress space or normal and shear stress space. So if you write it in principal stress space, that is how it looks like. If you write normal and shear stress space, that is how it looks like. The failure surface in principal stress space for maximum for Mohr Coulomb theory is this, but the failure surface in sigma tau space is this. Okay. But we mostly deal with the principal stress space. That is why we write the equation in this form. Okay. Any questions here? No questions, right? Okay. Now let me compare different failure theories. This is sigma 1. This is sigma 3. So let us say I am talking about an even material. So even material, even material. What is the even material? SUT is equal to
SUC.
minus SUC is equal to minus SUT. Correct? So let us say this is my SUT, positive direction. So for corresponding to sigma 1, minus SUT will be this one. That is my SUC. And this is my SUT. Similarly, this is my SUT. That is my SUC. I agree with that. So if you are doing maximum, if it is an even material, my maximum normal stress theory, what does normal stress theory say?
That stress difference should not be more than sigma y.
Yeah. So my failure surface look will be a square. That is my maximum normal stress theory, isn't it?
Yes, sir.
For an even material. For an uneven material, so all that I need to do is identify my SUC. Let us say that is my SUC instead of tension this much, but in the compression, that is my SUC. Then the maximum normal stress theory becomes what?
Rectangle, na, sir.
It will
Oh.
become a square still, but it is shifted. The origin is not anymore the origin. It is an asymmetric square, isn't it?
Yeah.
Right, that is your, so for these are the points for maximum normal stress theory for even material, and those are the points for boundary points for maximum normal stress theory for uneven material. Correct? Now, if you are doing more Coulomb theory, then for an uneven material, more Coulomb theory will be that will be your more Coulomb theory. All of you agree with that? The blue is more Coulomb for an uneven material. For an even material, how does more Coulomb look like? For an even material, the more Coulomb will be,
symmetric hexagon.
yeah, will be very similar to our
Ductile.
maximum shear stress theory, except that the boundaries are not ultimate yield strength, but it's ultimate tensile strength. So let me write, this is more Coulomb even. This is more Coulomb uneven. This is maximum normal stress theory even. This is maximum normal stress theory uneven. Okay? Now, people have looked at it and yeah, it looks good, modified, more Coulomb theory is doing job. But they have done some experiments, and in the experiments, it is found that the more Coulomb theory, while it is doing a good job, by doing some modifications, it seems to be doing a better job. So what is the modification that they did? The modification that they did is the following. Instead of connecting this line from here to here, what they did is they have done up to here. And this they have connected. Similarly, here, instead of connecting directly SUT to here, and that is my modified mode. And this seems to represent experimental data much better. Okay, so let me show you the slides. So this is your maximum normal stress theory for even material. That will be your maximum normal stress theory for uneven material. And that's your more Coulomb theory for uneven material. That is modified more Coulomb. So this is more Coulomb for even uneven material only. But this pink, the pink one, sorry, this is pink. Yeah, whatever color that is, it is for modified more Coulomb because this seems to match with the experimental data better. So you can see this. This is the experimental data for cast iron, gray cast iron. If you have used more Coulomb, this is the line, more Coulomb line. But the modified more Coulomb is shown like this. Okay. So since the experimental data is matching better with the modified Moore Coulomb, people have said that, okay, if you Moore Coulomb is okay because it is going to be more conservative, and in order to save some material, now the suggestion is that instead of using Moore Coulomb, you use modified Moore Coulomb, which seems to match with the experimental data more closely. Okay, so that is the reason why the modification is suggested for the Moore Coulomb theory. And hence, the equations that we write for modified Moore Coulomb is going to be much more complicated, isn't it? Because you need to break it into saying that, okay, up to sigma UC is equal to, when sigma 3 is less than or equal to sigma UT, the failure surface is this. If it is greater than, then the failure surface equation will be this. Otherwise, we had one equation was doing that, but now you need to break the equation in this region as well as in this region. So that makes mathematical manipulation is going to be a little difficult, but otherwise, the idea is to ensure that it is close to the experimental data. Okay. Any questions here? So one important thing to note, when the data is in the first quadrant, the results between maximum normal stress theory, modified Moore Coulomb or Moore Coulomb are one and the same when it is in the first quadrant and the third quadrant. But if the state of stress is in the fourth quadrant or the second quadrant, then the results deviate, and hence you cannot use maximum normal stress theory. Because you can see in the fourth quadrant, if you are using maximum normal stress theory, for this data point, it is already failed, but your maximum normal stress theory will predict that it is safe, which is a dangerous thing. And hence you cannot use maximum normal stress theory for brittle materials, even for brittle materials. Okay. So now how do we calculate the, what do you call, factor of safety? Let us say if your state of stress is at point A, then you can draw a line and OA dash by OA will be your factor of safety. Similarly, if your factor, the point state of stress is at point B, OB dash by OB. If the state of stress is at point C, then OC dash by OC. And this equation, so for example, if you talk about OA dash by OA, you can see that, let us draw a vertically downward line and a vertically downward line here. The state of stress at A has some sigma 1 and sigma 3. And now OA dash by OA can be written as O to this distance by from here to this distance. Can I do that? So which means OA dash by OA is nothing but sigma SUT by sigma 1. Whatever is the value, sigma 1 corresponding to this point. Similarly, here also I can write SUT by sigma 1 corresponding to this fellow. But in this case, you cannot do that. So OC dash, you need to do a little bit more work. So in the case of ductile materials, when we are using von Mises yield criterion, we have something called so now if you want to find out factor of safety, you can use this formula. And if you, for a modified Moore Coulomb, then you need not worry about how the failure surface. If you just plug in the numbers, it will give you the stress, the factor of safety accordingly. Okay. However, we have seen in distortion energy theory a very nice thing, right? For an extremely complicated three-dimensional state of stress, you have something called an equivalent stress, which is like a one-dimensional stress, and you are just comparing that equivalent stress with the yield strength of the material to say whether failure is happening or like. Can we do a similar thing even for brittle materials also? So people, Norman E. Dowling has come up with this prescription, wherein he said you can come up with something called an effective stress. And when this effective stress becomes equal to the ultimate strength in tension, although the ultimate strength in tension and compression are different, now he came up with a prescription where you compute the effective stress and compare that effective stress with the ultimate strength in tension. And if it is less than that, it is safe. More than that, it is unsafe. How do you go about getting these effective stress? The effective stress sigma tilde is the maximum value of these C1, C2, C3, sigma 1, sigma 2, sigma 3, where sigma 1, sigma 2, sigma 3 are principal stresses. C1, C2, C3 are computed from this, in which SU2 is the ultimate strength in tension, SUC is the ultimate strength in compression. So if you write a program, then the computer program can actually calculate these things, and it is much easier to compute the factor of safety by using this formula, the ultimate strength divided by the effective stress. Similar to one misses yield criterion, where the factor of safety is sigma y by sigma equivalent. A similar formula can be used for brittle materials also. Any questions here? Okay,
Here
there
in
are
the
no.
final,
Yes.
in the final formula, we are considering only the tension ultimate strength, not compression.
That will be, yeah, the prescription, he derived this equation, so he calculated C1, C2, C3 in such a way that eventually if you do this, that will give you the factor of safety. You can derive these equations, but if you use C1, C2, C3, then maximum of them, and then if you compare it with the ultimate strength in tension, that will give you the factors. Okay?
Okay.
Again, I don't expect you to remember this formula, as we have discussed in yesterday's class. This will be provided. Okay, any more questions? Okay, now let's solve this problem then. Don't say yield strength, take this as ultimate strength in tension, ultimate strength in compression, these values. So, any luck?
Sir, 2 minutes, sir. We are working, sir.
Hmm.
So principal stress are coming around 2400 and minus 600, right? If I'm not wrong.
2400 minus 600 makes sense because 2400 minus 600 is 2400, 1800, and that
Yeah.
means 1800 is making sense.
Right, sir. And after that, probably, let me think, sir. I'm a bit stuck over here now.
If you have sigma 1 and sigma 3,
Yeah.
now what is the equation? Sigma 1 by ST minus sigma 3 by SC
Right, sir. Right, sir.
is equal to 1, right? Yeah.
Right, sir. Sorry, I was not able to see the formula, so I could not get the intuition, sir. I'm sorry for that.
No problem. That is the formula.
Just can you repeat, sir, once again, please, sir? Sigma 1 divided by? I'm sorry.
Yeah, that is the, you can see the screen.
Yeah. Minus sigma 3 by SC is equal to 1. Okay, cool. So 2400 divided by 16400. That is 2400 divided by 16400 is 0.146 minus sigma 3 is minus 600 plus 600 divided by ST is 520, sir. Okay.
So if you have to write the equation, sigma 1 by ST minus sigma 3 by SC is equal to 1 by N. That is factor of safety, 1 by N. Then you can calculate the factor of safety.
Okay, 24 divided by 5250 is 2 plus 600 divided by 16400. So 0.03 is equal to 1 by N. 103 plus 0.45. So 1 divided by 0. So 2.08, sir, approximately.
Yeah, I don't know the value, but let me see. I have to see the slide must have the value. Yeah, 2.1875, because don't worry about it, because this is computed for the modified Mohr Coulomb.
Okay.
So modified Mohr Coulomb will have a higher factor of safety, no, compared to normal Mohr Coulomb. So more modified Mohr Coulomb can be calculated using this formula.
So this we should not remember, sir, for the exam.
No, but sigma 1 by ST minus sigma 3 by SC should be remembered.
Noted.
Sir, can you explain from the formula how we are getting the factor of safety, sigma 1 by ST minus sigma 3 by SC?
So the factor of safety formula will be, if it is equal to 1, then see, this, if this is equal to 1, then it is exactly failing, right?
Yes,
Sigma 1
sir.
by ST minus sigma 3 by SC equal to 1 means it is exactly failing. So if you want to include factor of safety, it will be in the denominator 1 by n. So the equation will be sigma 1 by ST minus sigma 3 by SC is equal to 1 by n. And then by plugging in these equations, then you will get the factor of safety. You can see that by, let us say this is ST is equal to ST and SC are same, right? I would like you to go through this equation. Okay. Sigma 1 minus sigma 3. So the fact tau max is equal to sigma ys. That is when failure happens. Do you agree?
Yes, sir.
Tau max is when tau max is equal to shear yield strength. That is when failure happens. So the factor of safety will be sigma ys by tau max. Do you agree or not?
Yes, sir. Sigma ys by 2 max.
Tau max. What is tau max? Sigma 1 minus sigma 3 by 2. Tau max
Yes,
is
sir.
sigma 1 minus sigma 3 by 2. What is sigma ys? Sigma y by 2. So your factor of safety will become sigma y by sigma 1 minus sigma 3. Factor of safety will become sigma y divided by sigma 1 minus sigma 3. Or is that clear? Maybe I will write down.
Yes,
Maybe
sir.
if I don't write down, maybe it is difficult to follow. Let me go back to my. See, now let us look at the maximum for an even material. Let us forget about odd material. For an even material, what is the formula? Sigma 1 minus sigma 3 is equal to ST. That is the failure criterion, right? So the factor of safety will become ST by sigma 1 minus sigma 3. Do you agree? Or this can also be written, the equation can also be written, sigma 1 minus sigma 3 is equal to ST by n, or sigma 1 by ST minus sigma 3 by ST is equal to 1 by n. Now ST and SC are not same, so sigma 1 by ST minus sigma 3 by SC is equal to 1 by n.
Understood.
Okay.
Yeah.
Hmm.
Further, we can bring n, we can take it to that side, and we can bring all the terms to the denominator of 1 actually.
Any which way, but see, the equation is same, which is only rearrangement of numbers. So now your
Yeah.
factor of safety will become SC times ST divided by sigma 1 SC minus sigma 3 ST.
Okay. Got it.
That is the equation that you would have seen in one of the discussions that we have. Okay.
Understood, sir. Yeah, thank you, sir.
So in this ultimate compressive strength, do we need to use with negative sign or
No,
positive?
it is coming with the negative SC value. See, when you are looking at the equation, no, then you have to calculate the actual value of SC.
So
Negative.
it's
If it is minus, no. So, for example, how did you do for a maximum shear stress theory? Maximum shear stress theory is what? Sigma 1 by ST minus sigma 3 by ST. Correct? Is equal
Yes,
to
sir.
1. Did I use negative symbol here for ST? That is embedded in this equation. This negative
okay,
symbol.
understood, sir.
Yeah. Okay. I think we will stop it here, and we have uploaded the second assignment, which will also be helpful for your preparation for the exam. Okay. That is why I have made the submission deadline as 7th November, so that you are prepared by solving all the problems. You are prepared for the exam on 8th November. Okay. I hope you have
So the
received that email from our code office.
Yes, sir.
Uh,
We received.
Yeah.
We received.
Yes.
So exam will have only numericals or it will be theory based also? Just, I'm sorry to ask this question, but
No problem. Mostly it will be numerical.
okay, sir.
Mostly numerical. Yeah.
Sir, the portion is still today, right, sir?
Until today. Yes. No, the brittle failure. Yeah. Until today it will be there. Yes.
Sir, please, if possible, can we make it till ductile only? Because I'm sorry to, it's just
No,
the
but-
discussion, your discussion,
why?
sir, but sir,
It will be better, sir.
23 batch, sir, basically we are like too many things to like cook this semester. Basically we have a project, full blown project, then we have computational methods, and of course, sir, this FAD.
How come you are doing computational methods now?
So it's,
Yes,
it's
sir,
like
it
that
is-
only, sir.
Huh?
Yes,
It's like that only, sir.
No, but that should have been the first semester course, no?
This is
There was
Sir,
a
that-
there
that is
was a
Based on the professor availability, they have shuffled the subjects, sir.
Oh, okay. All right, fine. Okay, so I will keep it only up to ductile failure theories. Fine, no problem.
Thank you, sir.
thank you so much, sir. Thank you so much.
Okay. All right, bye. We'll see
Bye,
you
sir.
next week. Yeah, bye.
Thank you, sir.
Thank you, sir.
Bye.
Thank you, sir.
Thank you.
Thank you, sir.